Okay, it is my pleasure to introduce you to my guest on this episode on Pratidwani, uh, Professor Kasturi Saha. Hi, Kasturi.
Hello, hello. Hi,
So,
Pawan.
for listeners, Kasturi is an associate professor at Indian Institute of Technology, Bombay, and she did her PhD from Cornell University. Subsequently, she was a postdoc at MIT, and before all that, she did her masters at IIT Delhi. And prior to that, she was at St. Stephen's College in Delhi. And Kasturi has been doing some fantastic work in the context of solid state quantum optics and nanophotonics, which also includes some fascinating work related to nanodiamonds. And that is something which we're going to listen to. For listeners who have just tuned in, this is also a kind of relatively new segment what we have introduced, which is called as Emergence, where we're going to talk a little bit more about an emerging researcher like Kasturi and her emerging research, which includes some very interesting aspects of nanodiamonds and also allied research areas. So, with that introduction, I would welcome Kasturi to Pratidwani.
Thank you, Pawan. Yeah, I am happy to answer any of the questions that you have in mind, and I'm so happy that you invited me in this segment of yours. So I have heard most of the other previous episodes, and I'm really looking forward to talking and chatting with you. Yeah.
Yeah, it's my pleasure. It's my pleasure. So, Kasturi, give us a kind of an overview of your kind of biography in terms of where you grew up, what was your kind of education, and then we'll also discuss about your research. Yeah.
Yeah. Okay. So it's a long story now because that takes me back all the way to school days because I grew up in a very modest family in central Calcutta.
Mhm,
My home is in central Calcutta near Esplanade, and people would, if you're familiar with Calcutta, you would know that that's really the heart of the city.
mhm, mhm,
Yeah, my home is there, and I come from a family of doctors and engineers, and so definitely science was really the direction to be. If you're growing up, you would either become a doctor or an engineer. uh,
mhm, mhm,
so I had similar motivations, and I always liked medicine a lot, and I was very good at biology. So
Ah,
of course,
okay, okay.
yeah. So I wanted to
Mhm,
be a doctor, but at some point of time I realized that I really didn't want to be a real doctor because my father, my uncle, and my aunt, everybody who are doctors, they would
Oh,
say that, don't become a doctor because you're just going to keep studying and studying and studying, and you'll never really enjoy your life. And so I said, okay, maybe there is a different way, and I wanted to sort of get into research in medicine,
mhm,
and that was
nice.
really one of the things I wanted to do. But then, somewhere in 1995, when we had this culture of discussing science at home, and
Mm,
my family, everybody would get together and we would chat about different things going on. And in 1995, Bose-Einstein condensates, got the Nobel Prize,
mhm,
and I
mhm,
saw it on
mhm,
the newspaper, and that really made me think maybe I would like to do something like that in future. And so growing up, when physics was actually formally introduced to us, I started liking it because it was not math. And
mhm.
that's something I
Ah,
really sort of got into, was that I liked math but not so much
mm.
because it always seemed very abstract to me, and I could never relate to it as much. And you wouldn't sort of think that I'm actually a much of a art history person that way.
Mm, yeah,
I
yeah.
actually deeply appreciate all of that, and as growing up, I think that was one of the things that really put me thinking about physics. And so although at 11, 12, you're looking at professional careers, so engineering or medicine would be the right choice. But as it so turned out, I did not clear a single medical exam. So neither West Bengal JEE, neither NEET, none of them, none of them. I was exceptionally good at bio, but I did not make it to a single exam. I did not clear JE as well, and so my mom was very, very disappointed, and I think everybody in my family was. But I did, clear West Bengal JE for becoming an engineer, and
Mm.
my rank was that I would have become a chemical engineer. And I didn't want to study chemistry at all by any means. So at that point of time, I decided to apply to St. Stephen's College. India today had this top 10 colleges. Uh,
Yeah, yeah.
so I just looked at it once, and I told my dad, look, this looks okay. I think I am okay with applying here. And I picked up the form for St. Stephen's. I only applied to the physics department. I did not. My dad said there are two options. You can apply either to math or chemistry as a backup. I said I don't want a backup. If I have to do this, I only for physics. I don't want a
Nice.
backup. Yeah, so that's how I went to St. Stephen's, and then of course. St. Stephen's was a very intimidating place, to be honest. First time out of home,
Mm,
I
mm,
had fantastic seniors. I think you would know many of them. And like Arijit Pal, and they
mm, mm.
Chadri, and we had exceptionally bright. Manas Kulkarni, who's now
Oh,
my
Manas.
guest.
Yes, yes.
Yeah, so they're exceptionally bright people. We had a Saturday Feynman Club discussions,
Mm.
and I was like, oh my god, what is going on? And I was very intimidated, to be honest. And they were always talking, and that was the era of string theory. And I remember there were talks on string theory all the time, on astrophysics all the time, and people who came in to do physics always wanted to do astrophysics, and I didn't
Mm, mm,
could not relate to that at all. Somehow I was never an astrophysics person.
mhm.
Strangely, most people think of brief history of time, or whatever, and you're always motivated by all of this, and I never was that kind of a person somehow.
Nice.
So
Okay.
yeah, I mean, interestingly, somehow finding my groove in there was quite challenging.
Mm.
But I remember when I was finally graduating, Professor Fukan, Dr. Fukan, he once told me that no Stephenian has ever died of hunger, so neither will you. I said, okay, maybe there is a path. And then by that time, I had already, gotten admission into IIT Delhi. And so I was like, yeah, maybe it is okay. I will be fine. So at that time, of course, when I was doing my BSc, I did interact with Professor Annapurni in DU, and I did
Yeah,
my
yeah.
BSc project with her on surface plasmons. And
Oh,
she's
okay, okay, okay.
really a big motivator. And she said,
Mm,
why don't you do experiments? You will like it. It's much more, something that you can work with your hands on. And that's where I
mm,
deeply appreciated, experiments in photonics, in optics,
mm,
and I was
mm.
exposed to that, and I started thinking maybe that is what I wanted to do. And that's why IIT Delhi was one of the choices, very natural
Choices.
choices for me, because optics is one of the big directions in IIT Delhi. And so I thought that why not. And I also had
Mm.
seniors in IIT Delhi, like my college seniors like Archana and Nishtha were already there. So I thought, okay, well set, I don't have to worry too
Said.
much about it, and plus no Sifanian has ever died of hunger, so I'm okay with it. So yeah, I went to IIT Delhi. And then of course it's a trajectory that most people sort of figure it out by themselves. And I also liked it, trying to do things by hands on kind of things. But it's kind of crazy how things turned out, because I did lots of summer projects and I think at some point I did mention to you that I
Mm,
encountered Rai Chaudhary,
mm,
I
mm,
as one of my summer intern guides. And I did crazy sort of
mhm.
manufacture whatever synthesis of
Yes,
magnetic,
yes, yes.
yeah, of magnetic nanoparticles. And at that time, AKR was in had just moved to SN Bose, and
Mm,
SN
mm.
Bose was not even well set up. So we had this chemistry lab in one corner of the field. It was like a little room, and I was doing some
Okay.
experiments there, and trying to make some magnetic nanoparticles. I really enjoyed it, actually.
Mm,
And it
nice,
was also
nice.
home. So then I went in the following summer, before moving on to IIT Delhi. In that summer, I actually went to IISc.
Yeah.
And at that time, remember, I always liked biology. So I thought maybe why not bio and physics seems to be a
Mm,
very good combination. And XRD was a direct way to get into that kind of work.
Yeah.
And so
Yeah.
I actually applied, and in the IAS fellowship, I worked with
Mm.
Professor MRN Murthy,
Oh,
and I
wow.
made
Okay.
lysozymes, and actually did X-ray diffraction. Uh,
Nice. Nice.
that sort of was a nice thing, but at the same time I realized that XRD was very, very boring, and to be honest, it was very boring. But I think I was not exposed to the kind of power it has over
Mm.
developing drugs, and which is what we see even in nowadays. But at that time I didn't want to do that anymore. So I said, okay, what's the next thing to do? And then came TIFR. Next
Mm.
summer
Mm.
I went to VSRP to TIFR, and Professor Venu Uppal, who's now the director
Vinegar.
everywhere.
Yes. Yes.
At that time he had, he was there. I was actually working with Professor Vengur Lekar, uh,
Mm. Yes. Yes.
who
Yeah.
was there
Yeah.
at that time, head of the
Mm.
department of condensed matter, and Mandar and Gopal were my basically the mentors of
Mentors.
VSRP, and Gopal I worked directly with. So Gopal really
Nice.
taught
Nice.
me how to hold a lens, how to clean a mirror, how to work in an optics lab. So I
Nice.
got it, so he was truly my first mentor in a real
Mentor.
scientific, direction, and he taught me how to make slides, which I
Nice.
think I am forever indebted to him, because he was like, everybody was writing the report, and
Mm.
Gopal told me that don't write the report first. First, make your
Mm.
slides and then write
Yeah.
your report, because then
Really nice.
everything will just flow very nicely. And I, to date, take this to my students. And whenever we are writing papers, I first tell them, you make the slides, make your figures, and once it's done, you know the structure of your story, and it will just flow automatically. So I think
Absolutely.
that
Absolutely.
is so that was Gopal. And then after that, of course, I realized that I wanted to get back to BCs, which is where the original
Yeah.
thought process was. And I applied to various places in US. I got into Cornell, which is physics department is the best place to do condensed matter
Yeah.
experiments. And I had in mind that maybe Dan Ralph, I had heard from Mandar,
Mm.
Dan Ralph was his advisor. So I was very excited that maybe I will get to work with Dan Ralph. And then there were a few other people like Itai Cohen, who was working with in
Mm.
biophysics, and he
Biophysics.
does
Soft
all
matter.
these
Yeah.
soft matter, soft condensation. So it was kind of things that I really liked and wanted to explore. So Cornell was the perfect place. Nobody told me, of course, that Cornell was a very cold place. And I did not bother to find out either. So, yeah. And then I went to Cornell, and I realized that they had just hired a person who was going to build up a BEC setup.
Mm.
uh,
Mm.
Mukund. But as it so turned out that I got exposed to Alex Gaeta's
Mm.
group in Cornell, and he said, well, we don't work with cold rubidium atoms, but we do work with hot rubidium atoms. And I did, we had to write this kind of a short sort of summary of somebody's experiments, about somebody's
Mm.
experiments. And I worked with Alex's group for
Mm.
that maybe 1 month or so, and I wrote a little piece on what the experiments they were doing. And I realized that this is the kind of thing that I would like to do. And that's where comes Professor Saikat Ghosh, magically.
Yes. Psycho. Yes. Yes.
And I still remember the coffee I had with Saikat, where I was deciding between BCs and Alex. And
uh,
Dan had already told me there was no position, so no chance. So then BCs and Alex. And I said, hot or rubidium or cold rubidium atom? Which one do I choose? And Saikat sat me down with a cup of coffee and said, look, here's an experiment I have built. And Saikat actually built that hot rubidium experiment.
yes.
And
Yes.
said, I really think there is a future. And
Mm.
there's nonlinear optics, and you can really do many things with it. You can go to single photon level. And I was quite excited, and I believed Saikat somehow, because he had this magical power of making you believe that there is something truly about it. And I really believed him, and I was convinced that this is what I wanted to do. uh, so thankfully I had made that decision, because it was a fantastic, I think, choice. And I have ever since loved, what I did for my PhD. Although it was a sort of a, different kind of experiments I interacted, and I was the only female in my group at that time, 18 boys,
Wow. Okay.
one one girl at that point of time. So it was quite an interesting challenge. And then, of course, PhD, for 4.5, 5 years I had already done a
Mm,
lot of
mm.
work. And so much so that Alex was like, I don't know what to write as the title of my thesis. If you read my thesis title, it's like nanophotonic structures, and I was like, it has everything. So pretty much. And then I sort of went into MIT doing something different, because
Mm,
I just thought that it was good thing to do something completely different.
mm, mm, mm.
Yeah, and now I'm doing NVs. So
Anyways,
yeah.
fabulous, fabulous. It's so interesting that you actually also had very good exposure in laboratory kind of sciences, which is a very important component in your own research. But you also been able to blend very interesting research in terms of also some theoretical perspective, because some of your recent papers also have been exploring some ideas in the domain where it can be applied to quantum processing and things like that.
Yes.
Give us a kind of a gist of your current research, Kasturi. What
Hmm.
kind of research problems and questions you and your group are asking, and what is the direction your research is heading towards?
Yeah. So there are basically, my group is focusing primarily on quantum sensing.
Hmm.
And that's been the theme that I have started off with right from day one in IIT Bombay. I've I've been interested in developing quantum sensing technologies, and mainly tools,
Hmm.
and from scratch. So we build everything from scratch in our lab, and pretty much we are tool builders, so to
Hmm.
say,
Hmm.
for quantum sensing. So that's the main overarching theme for our lab.
Hmm.
And
Hmm.
then the main the material of choice is color defects in diamond, which is NV
Hmm.
center, silicon vacancies. These are the kind of materials. And then now we are also looking into 2D materials like HBN, and other sort of 2D materials. And so the main idea here is that we want to look into aspects of quantum sensing for imaging. And
Hmm.
that
Hmm.
again sort of ties back to my original dream of working and contributing in biology.
Hmm.
And
Hmm.
so imaging, MRI, sort of is always been the main sort of thing that biologists have been interested in. And I have always been looking for problems where I can apply tools that I built to biology. And so that's
Hmm.
where
Hmm.
this MRI kind of tool development, 3D imaging with NV centers, is one of the main key directions in which we are working towards. And that's where also nanodiamonds also come in, because nanodiamonds are also useful for looking at very localized problems within cells, and trying to see chemical sensing within cells or temperature sensing within cells. uh, and we want to look into live cells. So that's
Hmm.
the
Hmm.
direction in which we are going, and where we want to build setups for investigating fully live cell kind of environment, and want to use the quantum sensing aspects for live cell imaging. The other sort of completely different kind of applications we work on are hybrid quantum devices. So these are
Hmm.
single photon emitters, development of single photon emitters, development of hybrid structures, photonic structures. And this sort of ties back to the kind of things I did for my PhD, where we worked with waveguides, nonlinear optics, and trying
Hmm.
to
Hmm.
see if we can connect that world with photonic crystal structures and quantum emitters, and development of quantum emitters. So that's the other direction in which my group really focuses on. So mainly those two, and connecting them, of course, is the theory, underlying theory, that
Hmm.
we have
Hmm.
to develop. Because if you want to be a tool builder, you have to essentially understand the key aspects of not just the material but how they interact with each other, and how to simulate them and understand the the properties before you can really jump into tool building. So that is why we focus also on aspects of where we want to apply the tool to, so that that gives us the idea of what are the necessary requirements for or specifications that a tool needs to have if I want to tackle a kind of class of problems.
Problems. Yeah.
Give a
Yeah.
specific example, like we want to develop tools for this hybrid quantum structures, right? We want to also
Mm,
develop
mm,
hybrid quantum structures are useful for quantum nodes, and this is something that
mm,
we everybody is sort of talking about, where you want to have quantum memories and as to act as quantum nodes. And how do you really interact and store so for that you need to have electron spin. The nuclear spin is the really the memory. So you have to
mhm,
have these understand the mechanism of how to protect the nuclear spins, how to protect the electronic spins, and interact with them at the same time. So some of our recent work has been looking into how to interact, look into these interactions and develop the theory for it. And also on the simulation side, we look into development of photonic structures. So
mm.
pillars, cavities, and all of these are very integral part of our research. So that's where all of this simulation and sort of plugging in sort of put comes together, and then we take it forward in the next step towards experiments. Yeah.
Wonderful, wonderful. In fact, I should mention to the listeners that I actually am also, part of her collaboration when we actually had a very nice paper together, and I very highly benefited from the intuition what Kasturi and her group actually had on the nitrogen vacancies in diamond, and some very fascinating things. One of the things, Kasturi, in your research where you have been already kind of working on, and also have built some very fascinating instrumentation, is related to magnetometry.
Yes.
The problem of measuring magnetic fields at extremely small scales, submicron and micron scale, is kind of an open challenge, and there are some very interesting things what your group has done. Could you please just tell us just about what you people have done?
Yes, absolutely. I think, yeah, so NV centers are really one of the key methods used for doing room temperature magnetic field sensing.
Mm, mm,
Typically, NV centers have been used to measure as low field as picotesla,
mm,
magnetic field levels. And just to give a feel to the audience, the Earth's magnetic field is about 50 microtesla, and so we are measuring
mm,
fields at very very low levels here. So the idea is not just to measure the field but actually to image
mm.
the field and
Image the field.
image the field and reconstruct the entire vector nature of the field in different kind of samples. And that is so biology is one aspect, but then there are these all these condensed matter systems that really excites me, because it
Mm,
really
mm,
merges with the kind of things that I'm interested in studying, where you have electron electron interactions which can be mapped at the micron level or submicron level, in different kind of superconducting samples, for instance, or even these different 2D materials or 2D magnets,
mm,
2D
mm,
ferromagnets. All of these kind of different samples exist, where people have been using methods like squid or even scanning magnetometers for
mhm,
looking at
mhm,
different magnetic field images. However, some of the challenges there is that you can't really do these at a fast time scale, and many of the effects that people have observed are either through transport or through squid or scanning tunneling, scanning
mm,
magnetometers. There it takes a long time to actually image the entire sample. So what we have built in our lab is essentially a wide field magnetometer, so image,
mm,
it's a quantum diamond microscope as we call it. So
mm,
you can image an area of about say at least 100 micron by 100 micron, with a
mm,
resolution of 1 micron. And now we are trying to push it down to the diffraction limit, which is 250 nanometers in this case. But even going beyond that and really going sub diffraction, where we want to go super resolution. And so now we are actually looking into extending the quantum diamond microscope into super resolution limits. So
Mhm.
that is one of the big challenges, where you just not just want to do super resolution in static case but also in temporal. Now in the past
Mhm.
6 years what we have developed is the microscope, so that you can measure dynamically varying fields, and that's where all the interesting sort of noise properties and all of these actually come into the, for various kind of samples you can look into it. uh, so dynamic variation of magnetic fields have interesting information, and
Nice.
that's the main instrument that we have developed so far, and now we are trying to push the resolution as well, and try to
Mhm.
get to sub 250 nanometers, so that we can get very high spatial resolution as well as temporal resolution.
Temporal resolution. Wonderful. So the ultimate aim is to also introduce these kind of imaging agents into kind of biological environments, and any other kind of environments you are interested in looking at this.
Currently, these are the main two focus areas. So, condensed matter
Mm,
samples as well as
mm,
biological samples. And in biology, the main thing is that it's just really you want to do neuronal imaging
uh-huh, mm,
at the single neuron sort of resolution, and try to track each of these spiking neuronal potentials, which essentially give
mm,
us clue of how we function, how our brain
mm,
functions. So, if you can correlate how signals are propagating inside your brain, and if you could somehow image the potentials, then one can actually try and figure out with correlate with the kind of impulses and whatever input you give to the brain. So whether we are walking, talking, how our brain really functions, and that's a very blue sky kind of a goal, but
mhm, mm.
that's the main sort of direction in which we are pursuing and building, developing the image of form. Yeah.
Fascinating, fascinating. So, give us a kind of background of how did you got interested in this kind of problem? What really led to this kind of aspect of looking at nanodiamonds, magnetometry, etc. Could you just tell us a little
Yeah,
bit?
sure.
Yeah.
So, like I said, I did a PhD in nonlinear optics, and then after
Mm,
that, I had, Alex's group is a prolific group, and we were working on developing spectroscopy tools with frequency combs. And if you know that
mm.
frequency combs is one of the best ways for doing spectroscopy.
Spectroscopy.
So
Yeah.
that was my PhD work, where we looked into temporal aspects of the frequency comb, and I started thinking of how to use frequency combs for spectroscopy. But then once I graduated, I there was a thing in our group that you have to do something different.
Mm,
You
mm.
don't want to be Alex's competitor, rather you want to be a
Mm.
friend. And that really pushed me into seeing what are the possible directions in which I can move into.
Moving
And
to
at
okay.
that point NV centers were there, but people were talking about it all the time. But I mean, I was not too familiar, but I
Mm,
knew that
mm,
it was around, and so I started applying. When I was applying, I luckily got into MIT with Paula,
mm,
and
mm,
she at that time was very interested in developing these MRI kind of applications for NV centers, and developing magnetometers for neuronal signals imaging. So, and but my project was slightly different. I was working on gyroscopes and development of gyroscopes, and but however I kept a tab on that experiment. And in Harvard, all Harvard MIT community, it's very interesting how they function, because the group meetings are all open, and anybody can
mm.
go and sit in somebody's group meeting. And so often on Fridays I would be in Ron Walsworth's group meetings, because I was always
Wow. Okay.
interested in what the people there are doing,
Mm,
whether it's
mm,
condensed matter or whether it's biology. And Ron Walsworth actually happens to be the main,
yeah.
pioneer
Pioneer.
for this kind of experiments in applying in NV centers to biology. And he, in fact, had a room where they built a full MRI machine, and they were going to
Mm,
test the NV centers for biology. And so he has an active collaboration with Harvard Medical School on developing an
mm,
NV based magnetic field imager. So that was always on my mind, and I kept following all of that. And I thought, why not? When I was coming back to India, anyways, India did not
mm,
have any NV center groups. I will,
mm,
I,
mm.
as you know, I am the first one to have set up this sort of things in this country. So. I mean, that was already there, and that really interested me. And I think this is a big potential, application domain for NV centers. So I started, working and thinking about it. Uh, and over time, I think I have, tried to exploit many of the advantages of NV centers for various different things. But that has been the main interest, and how it got me
Interesting.
interested into this. But I think it's the main thing about, Harvard, MIT's open, discussions with each other, where,
Mm, mm,
there's a term called frenemies, where
mm,
you are openly competing with each other, but you're friends with each other, and in a very deep way.
mm,
And I
mm.
have seen how Paula interacts with, Ron, or with Lukin, and all these,
Yeah, MD looking.
amazing groups, where each of them are doing fantastic work, but at the same time they also help each other bring out
Mm.
the best in them. And I think that really motivated me, and I think that's also
Wonderful.
culture that I would like to see here somehow.
Yeah, yeah, absolutely, absolutely. That's actually a good kind of benchmark to have, because that is also a very nice way of doing science, where you not only share resources and knowledge, but also have a healthy competition in taking things further. So one of the other aspect which is also very interesting is that you have been able to also foster very good collaborations, not only within IITs, of course. As I mentioned, we also have collaborated.
Mhm.
One of the key elements of really doing work and taking the kind of ideas and broadening it would require talking to other people and broadening the scope of the research. And you have done it effectively by not only collaborating with fellow experimentalists, but also with uh, theoreticians and others. How did you go about this? Because this is important, especially for people who are really starting, or even for that matter, postdocs and PhDs. They need to actually get a gist of how do you go about doing it. Could you please tell us?
Yeah, I think that's interesting. It's a very
Mm,
interesting question,
mm,
because during my PhD, actually, I had seen Alex collaborate very effectively with Mikhal,
mm, mm,
who's also his
mm,
wife.
mm,
But but he was very, very skeptical of collaborations. Let me tell you, very
mm,
honestly. And
mm,
we've had
mm,
many discussions where he would say, your collaborator has to be a person who brings in something very complementary.
mm, mm, mm.
And you have to work together so that you come up with something that is mutually beneficial.
Mutually
And
beneficial.
if it
Yeah.
if it is not mutually beneficial, it will just fall apart.
Mm,
And
mm,
so that is one of the things that I have always kept in my mind. I have also seen Paula interact very nicely, very effectively with many people. And the main key aspect is that you have to have mutual interest, and
mm.
really be able to work out the details. And
Yeah.
the really the devil is in the details, because you must lay out what is your contribution to the project and what is somebody else's contribution to the project. And so that's where, my collaborations with experimentalists, with you of course, and
Mm.
with other people, with Shorbo, as well as with, with theorists like Sumiran Pujari. He is one of
Sumir, yes,
yeah,
yes.
Sumiran is my, theory collaborator. And Himadri, we are also working on. Sai
Mm,
is
mm,
also another theory collaborator. And there, the main the nice thing is that for me, it's more like, if I'm an experimentalist, I come with an experimental perspective. And
mm,
when I
mm.
tell my theory colleagues, and I'm like, I don't understand any of your hypothetical sort of, picture. You have to tell me exactly, this is my experiment idea, and I want to see this out of the theory.
Outside
So
theory.
I have a very clear conversation with my theory friends, and I tell them that, look, this is what I sort of look to get out of this.
Mm,
Then it becomes much more easier to interact going forward. And sometimes it actually goes into really this, abstract kind of theory, and we have done that kind of work where, I see no hope of that seeing
mm,
experimental light at all. But it is still worth pursuing and
but
keeping that as on the table as a future experiment, perhaps in maybe sometime far away. But yeah, I think the main key ingredient is trying to understand each other. If you really
mm,
want to
mm,
go forward, you have to be, as a collaborator, you have to be on the same page.
Yeah.
And
Yeah.
and that's not easy at all, because we all have our own ambitions and we all are
Mm,
busy
mm,
with many things, and it can easily fall apart. One thing that, on a day to day basis, one thing that I really like doing is having a meeting on a weekly basis, or at least a
mm,
bi
mm.
weekly basis, to keep things going. Because if it sort of goes, as okay, month has passed by and you somehow
Yeah.
lose interest and you get
Yeah.
busy, and
Yeah.
most of the time it's like people getting busy and into absorbed into other things, and you sort of lose the focus. It's important to bring that focus back, and have concrete sort of discussions, and I think that is what helps in collaborations mostly.
Absolutely. Very pertinent points. Broaden the scope of the discussion a little bit. Now that you already have kind of established your research at IIT Bombay, and now also you have a good grouping, not only in terms of the colleagues, but also you've built a very good group, both in number and also in quality, which is an equally important thing when you're doing experimental science. Because merely having good students, only small number may not actually be sufficient sometimes when you're working on some projects which are very good. What has been your experience, Kasturi? Now you've been here in the system for now roughly about 7 years now in India.
Seven
Yeah,
years, yes,
seven
closing on
years. So
7 years, yes.
which means that you now have reasonable idea of how the system works. Uh, so could you please let us know how did you go about kind of establishing your group, expanding on the work what you have already been doing? What is the kind of experience you had, both positives and negatives?
Yes. uh, well, it's a very hard question, I think, because it has been hard. It's not been easy at all,
Mm,
and I have to give a fair warning to anybody who's setting up a lab from scratch, that and having come from US, given
mm,
I
mm,
I have all my learnings have been in big groups. So Paula's, you
mm.
mentioned about number. I worked in Alex's group, and I joined that group was 18. Okay, 18, I was the 19th person
Oh
in
my.
that group. So it was a very large group with a lot of
Mm, mm,
postdocs, lot of PhD students, and very healthy sort of competition amongst the peers, and also helping each other, of course, and that
mm,
that
mm,
bond was very important. And Alex was very particular in choosing students, because he always said, if one person can destroy
mm,
your group, and
mm.
one person's sort of behavior can really ruin the entire nature of your group. And I have
Absolutely.
kept that in mind, and so that's why I think, when I started my group, I think I kept that in mind, thinking that I have to have a fairly large group, because you need to have and it's not just because I want a large group, but it is
Mm,
necessary
mm.
when it comes
Necessary. Necessary.
when it comes
Absolutely.
to
Yeah.
experiments. It is necessary because you need to have overlap between
Mm, mm.
students, so that there is enough information transfer. When you're
Info.
building an experiment from scratch, you have to have your first student transfer the same information to your fifth year student, first year student. So maybe whenever that graduating student has to have enough amount of overlap, so that they can really effectively transfer that information. Now I already told my students that I don't want to be
Mm,
again have to teach somebody how to clean
yeah.
optics in the lab. I don't want to do that. Definitely I am happy to help, and I really like going to the lab, and that is now my hideout, literally my hideout, that whenever I want to escape the world, I just want to go sit in my lab and do some experiments. Yeah, it has not been easy. So I think some of the key ingredients that have helped me is, of course, collaborations,
Mm,
trying to look for good students who also have not just and I think it's been very hard, because I'm in an electrical engineering department.
mm. Yeah.
I
Yeah.
don't get direct physics, background students. And it was one of the questions they had asked me, that, when I was applying, that will you get the students that you would like to have?
Mm, mm.
And at that time, I said confidently, yeah, why not? I mean, if they come with an engineering background, I do tool building. So that is what I'm
Yeah. Yeah.
interested in. I'm happy, they will, I can teach them the quantum mechanics that they need to do.
Mm, mm.
But
Yeah.
it's
Yeah.
easier said than done. And
So, yeah.
they come with some background, but literally they come with no background. That's, to be
Mm,
honest. You
mm,
have to teach them very patiently, and I feel that that's where my real contribution to the lab is. That
mm,
I
mm,
have to sit with them very patiently and tell them that, look, these are the aspects you need to learn. And they come with some, I don't have much of an expectation now. Previously I had, like 3 years 4 years ago, when I was
Mm.
much relatively newer to the system, I had very high expectations for my students. But thankfully, you wouldn't believe, I had two fantastic undergraduate students, Parth and
Mm.
Aditya,
Mm.
who were my lucky charm, I would say,
Yeah, yeah.
and Madhur. And then my first PhD student, Madhur was my first PhD student, and then
Mm.
of course she joined in. I think they were excellent, and both
Mm. Mm.
Parth is in Princeton now, Aditya is
Mm.
in a company now, and I think without them I would have really been not been able to get into it. I think the undergraduates. So initially it was the undergraduates who helped me build the lab, and then my
Wonderful.
PhD students actually took over, and now I have reversed it,
Mm.
where
Mm.
the PhD students are the key stakeholders in the lab, and the undergraduates are just there to help them and come and go. But initially it was the complete other way around, where
Mm.
my
Mm.
undergrads were my main sort of, and they were from physics. Happened to be I realized that it was not easy to just convert an engineer into a physicist.
Physicist.
Yeah, so
You'd rather do the other way around.
do it the other way around. So I took the physics undergrads, and I have a steady stream of physics undergrads who work with
Nice.
me. In fact, later on, Abhishek, who graduated this year,
Mm.
went to Caltech, also was has worked with me for a long term, 2 to 3 years. And I keep telling,
Mm.
so one thing with my group is that I have told them that when I take undergrads, I take them for a long term.
Mm.
I tell
Mm.
them from the very beginning, look, you come, if you want to get a paper in 1 month, my group is not the
Mm.
group. You
Yeah.
won't get it. At the end of 3 years is the earliest I can guarantee you that you will get a
Yeah.
paper.
Uh,
Nothing
yeah.
before that. And so I tell them that, look, my first year is only for learning. Second year, we will
Mm.
define your problem. And third year, you get to maybe touch
Yeah.
something
Yeah.
for my experiment, not before that. So that's how
Absolutely.
I'm very, very clear on that. And so, but however, I think that is the learning process that for me, it has been that how do you actually convince people that you should be doing this, and that is it's been very hard and very challenging. But on the other hand, when it comes to setting up a lab for experiments, and in India it is not easy at all, at
Mm.
all,
Mm. Mm. Mm.
especially with things are very slow. I mean, there are many processes which we can easily streamline, I
Mm.
feel. Especially purchase has become ridiculously hard. It was hard
Mm.
already, and it
Yeah.
has become harder
It's
now.
become true.
I
True.
think, and slower. So I think all of these can be easily ironed out. And if we really want to be a number one nation in the world for quantum
Mm.
technologies, given all the national mission and everything we have in mind, there are these basic things we have to actually streamline.
Yeah, it's just
And
streamlined. Absolutely.
I think this is one of the key things that I waste a lot of my energy doing things which I should not have to work about and
Mm.
think about
Mm.
at all. And I think that's where our country can really make a difference, by just doing the little bit of background work which is necessary to support its scientists, when it comes to laying out policies which are useful for faster
The
execution of projects.
execution of the projects.
Yeah.
Exactly.
So
Exactly.
I think would be, and of course learning the nitty gritties of how to work in a system is always challenging. And
Mm.
as a
Mm.
student, one thing that we are never taught when we are doing
Mm.
science is managing people.
Manage people.
And
Absolutely.
at the end of the day, all we are doing is actually managing people, right? My students have emotions, I have emotions. Balancing the people around me is also an emotional act, and at the end of the day we are not taught how to do that. And I think that's where all the conflicts actually come about, because I have an expectation that my students are working 24 hours into 7 days, whereas that is not a realistic expectation, because I never do that myself. So I think that is not
Exactly.
a realistic expectation. And I think that's where our learnings also have to be tempered. And it's been a very steep learning curve, I would say, for me, setting up a
Mhm.
lab from scratch, all the way from some of the challenges, I would say, is getting space. We had
Mm. Mm.
serious, I mean, I didn't have a lab space until 2 years almost. And
Mm.
so that's a very serious problem. And these are some things we can actually work out. These are,
Workout. Absolutely.
and I feel that these are some of the negatives about how some of the way I have had to deal with things in the last 6 7 years. And but one thing that has been very positive is working with people again,
People.
uh, and how my undergrads, magically, like I said, Parth and Aditya showed up magically on my lab, and I didn't go fetch them, they came to me. And in fact, Parth told me this one thing, that you should not go looking for students, only students should come to you, because then that is the only best students you will get, and that
Get.
is how you have your respect in the world. So this is what my students told me, that I said, you should not look for students. I said, okay, I will not look for students. Why don't you guys do good work so that students will come to me? So I think it's all about people skills and learning how to work with people. Yeah.
Fabulous, fabulous. Very, very nicely put. And it's an important thing. In fact, one should also kind of, chew this over a slightly longer period and understand. And if there is somebody who is interested now to join Kasturi's group, see, now there is an opportunity because they're doing some outstanding work. So we are almost about to conclude this thing. One of the aspect, Kasturi, which we also want to actually get a flavor of is how does a scientist relax? Okay, because I know people are busy, but I would request you to give us some recommendations about art, books, movies, and other things what you actually are interested in. Just give
Yeah,
us a kind of a
actually,
gist. Yeah.
I am. I'm a very sports person, actually, to be
Yes.
honest.
Okay. Yeah. 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 I
Yeah.
should mention it's not only arts but also the sports. In fact, yeah.
Let me talk
Yeah.
about art first, because that is
Yeah.
something I've
Yeah.
been doing since childhood.
Yeah. Yeah.
From 3 years of age, I have been in an art school, visual.
Wow.
Yeah, so
Mm.
I mean, I used to draw all over the walls, and my dad one finally
Mm.
said that, okay, we will put you in an art school, get
Nice.
trained, and become, really do something about it. So I have a visual art degree of 5 years from Prachin Kalakendra. Uh,
Wow. Okay. Great. Superb. No, in fact, if somebody is interested, one should look up some of the sketches what Kasturi has done. Fabulous. They're really. It's not like very small stuff. It's very very good stuff. Yeah. Yeah.
yeah, so visual art training was a very
Mm,
formal training. I even had courses and proper lectures and things like that. So that was during my school life. Then I of course continued towards watercolors, and I am primarily a watercolor person. And
mm,
then
mm,
of course came iPad, and so now I have
mm.
taking out your entire full scale of things
Scale
is
of
very,
things in.
yeah, it's very difficult. So then I have
Mm,
graduated now to iPad drawing, and
mm, mm.
but I still miss my watercolors. So yes, I do it
Nice.
when I do get time, but yes. So that's about art, and I've been doing it on and off when I get time.
Mm,
But
mm,
one
mm,
thing that when I went to Cornell, for my PhD, I was a very studious person in general. I have
mm,
always been throughout my life. So
mm,
when I
mm.
went to Cornell, I would see at 4 o'clock, everybody would vanish from lab. And I would wonder what is going on. Why is nobody there in the lab from 4 to 5:30? And I couldn't locate anybody. So
Okay.
one day, we had this postdoc Bongu
Mm,
Shim. He's in yeah. So he's in Binghamton University.
mm, mm,
I asked Bungu, what do you guys actually do? So he said, we play TT. Why don't you come?
mm.
I said, okay, but I don't know how to play TT. I have never played TT in my life. So he said, doesn't matter. You come, you see, and you play, and I'll teach you. So he's this Korean guy who's a lot of fun.
Oh
And
man.
I said, okay, Bungu, I will come. So, and it happened, and it so happened that, I had the keys to the TT room magically. You know why? Because Cornell had this thing that, we had a workshop.
Mm,
So
mm.
anybody who passes the workshop with an A grade used to get a key to the stock room, which was open 24 hours. So night time,
Oh.
midnight. So I was in great demand because I had the key to that. And then along with that key came the TT room key, which was also 24
Wow.
hours. um, so yeah, so then I said, okay, great, I will also play. So I didn't know anything from holding the racket to playing TT every day, 1 hour for 5 years. I think that was the most fantastic time because it helped me relax, and it really got me into sports.
Yeah.
And then I picked up there was a there was a funny conversation I had with Alex once, because in my fourth year in Cornell, I started taking a badminton class. and
Wow. Okay.
showed up on my transcript, by the way, because it was
Mm.
actually a class. So
Wow. It's a evaluated. Oh.
it's an
Okay.
evaluated class,
Mm, mm.
and guess who paid for it? Alex did. And so he looked at the transcript and said, I just paid $1,000 for your class. Why are you taking a badminton class? I said, I happen to, I want to learn this, and I thought it will be a good thing. You know how stressed out I am. I want to do this. So then he made a face and he said, okay. And so that's how it turned out. And I learned badminton first time in a proper formal way. And then I went to MIT and we had a formal. So Paula happened to play, volleyball. So she was very, very pro,
Oh.
training and
Mm,
everything.
mm,
And she said, why don't you? I saw that there was this badminton
mm,
coach who's also training at the
mm.
same time. Why don't you come? Okay, fine. And I trained in the evening. Actually, that was from 7 to 8:30 in the night, and often it would be 9
Wow.
o'clock, and Sid would come and pick me up, and
Yeah. Yeah.
so training was happening. And then when I came here and I heard that there is a formal place for staff and faculty to play,
Mm.
so I started playing badminton in IIT, and I do that every day. I played Inter-IIT last year. Uh,
Yes. Yes. And even one. I think you people
SMU and
won something.
semi-finals, yeah.
Mm,
And I think, uh, as an advice to people, I would say that sports, art, reading has always been there, because studious
yeah.
people
Yeah.
do
It'll
that
do
anyways.
that anyway.
Yeah,
Yeah, academics.
anyways,
It's a given. It's a
it's a
given.
given, right? You sort of know you do it. But I would say sports help me really taking my mind off something that is everyday mundane things,
Yeah.
and
Yeah.
all the stress. I think that 1 hour really helps me being, absolutely keyed in to the challenges, and trying to forget about all the stress and everything, and really helps in focusing in the future. So I think that 1 hour of play for me in the morning is very, very important. So I would say,
Wonderful. Wonderful.
yeah, that either TT or badminton or swimming or anything that you enjoy doing, I think it's very important to at least pick one sport,
Absolutely.
and do it very regularly, I think. Yeah.
If somebody is listening, please go and play. That is the
Yes.
most important thing. In fact, I can't overemphasize that because it's such an important part of kind of unwinding. Not only unwinding, it's also rejuvenating, right? Because it actually can really put you into a better frame of mind.
Absolutely.
Fabulous, Kasturi. Very nice. I am really thankful to you for kind of giving your mind, and also kind of discussing with us what is the kind of prospect of your research and all the other things. So I wish you all the best for your future kind of stuff. So you have any specific plans in terms of what you want to do in terms of where you're going to head towards in terms of research, and also any other ventures you're taking up?
Yeah, I think, one thing that I have not mentioned here at all is that I have
Mm,
always been interested in science policies. And at some
mm,
point
mm,
in my postdoctoral time, I told Paula that, I don't want to be a standard faculty. I want to do,
mm, mm,
so MIT actually has these science policy courses. So I wanted to
mm,
sign up for that. And there were also some training, prospects for working in Washington for science policies. And I told Paula, I don't want to apply for faculty and I want to do this. But it
mm,
turned out that you
mm,
have to be a citizen in
mm, mm.
US to actually apply for those science policies. And at that point, she also mentioned that one career option would be that you do your standard academic stuff, but at some point of the other, if you do well, people will actually pay attention to what you say.
Better motive, absolutely.
And then you can get into science policies. And it turns out that maybe that's exactly the things that are happening now. As you know, that I contributed to the DPR
Mm,
for
mm,
the
mm.
for the national mission. I think hopefully I will also be able to do contribute similarly towards science
Similarly.
policy in
Wonderful.
future. I
Wonderful.
think that's one of the things I would really like to do formally, and do it properly. And of course, the things that I've already been interested in, quantum sensing for imaging,
Mm,
of
mm.
course, that those are things that will continue, I think.
Continue. Yeah. Yeah. Wonderful, wonderful. This is something I did not know explicitly that you are interested in policy. Thanks to Pratidwani, I came to know about that. No, but it's a very important thing, Kasturi. It's very very important thing to actually have a good policy. for science and technology, and it should be driven by people who are doing research, and it should be also driven by people who have good understanding of gender equity. That's also an important aspect which is very, very critical in doing this. All the best for all the ventures what you're going
Thank
to
you.
take up. Okay. And I am extremely thankful again to you for joining me on Pratidwani, where we try to humanize science with Kasturi Saha. Thank you very much, Kasturi.
Thank you, Pawan, very much. Yeah, thanks.